All right, so now what we're going to do is we're going to talk about modeling with exponential and logarithmic functions, and we're going to start by solving literal equations for a particular variable. Okay, so again, this is just solving an equation for a particular variable in an equation. We're just dealing with log equations or exponential equations. Okay, so for part A, let's say we have this exponential equation here, and we want to solve for the variable x. Well, what we would need to do is we would need to take the log of both sides eventually. Okay, so let's solve this one here. Let's do part A. Okay, so again, the first thing I would do is we've got this constant here, this coefficient 100. We're going to divide both sides by 100 first thing because we want to isolate the exponential on one side. Okay, or if there's multiple exponentials, let's say adding or subtracting exponentials, we want to have an exponential on either side. But anyway, let's just deal with this. So first step, we want to isolate the exponential. So that would mean dividing both sides by 100. Okay, so when we do that, we get this. Now at this point, we want to take the log of both sides. Particularly, we want to take the log that has the same base as the exponential, in this case e. So we're going to do the natural log since they're using the natural exponential. So we're going to take the natural log of both sides. Now, using the properties of logs, right? So if the log has the same base as the exponential, then again, these are inverse functions of each other and they undo each other, and so the exponent just drops out. Okay? So in this case here, we end up with what? We end up with the natural log of p divided by 100 equals k times x. And then at this point, all we have to do is just divide both sides by the constant k. And when we do that, we get our final result for x. Okay? And so x is equal to that. Okay, now, let's do the same sort of thing with part B. But we're dealing with logs, so at this point what we're going to do is we're going to put isolate the log, and then we're going to exponentiate both sides. So let's do that. So the first thing, in this case, let's say we want to solve for d in this case. So d is in the argument of the log, so that's why we're going to eventually have to exponentiate both sides. So, but first, let's isolate everything. So we're going to first subtract off 8.8. So we're going to get L minus 8.8 equals 5.1 log d. And notice we're doing common logs. Now we're going to divide both sides by 5.1, right? And if we divide both sides by 5.1, we get L minus 8.8 divided by 5.1 is equal to the log of d. Okay, now we've got the log isolated on one side. Now we're going to go ahead and exponentiate both sides. And so the way we do that is just like this. Now, since we're using common logs here, let's just use 10. Okay, so if we do that, then we get this. We get 10, or we could use e, it doesn't matter, but we want to get rid of the log here. So we're going to use 10 to the exponent of L minus 8.8 divided by 5.1. And then we're going to do the same thing on the other side. 10 raised to the log of d. Now, just like in part A, now we've got a base of 10 and we've got a log that also has a base of 10. So we've got an a log function inside an exponential function that both have the same base. So again, they cancel each other out, and in this case, the argument d just drops out. So we end up with what? We end up with 10 raised to the power of L minus 8.8 divided by 5.1 is equal to d. And we're done. And that's how you do it.